Okay, so you're going to be graduating soon. This is what you want for graduation, right? If you want a car, the Dodge Challenger. But like anything else, make sure your substitution is correct. Okay, math, we do a lot of substituting variables for numbers, substituting functions for values. Okay, one of the hardest things is making sure that when you do your substitution, it's correct. So today we're starting by integration by substitution, and we'll talk about separable differential equations. So basically, the chain rule allows us to differentiate a wide variety of functions. When we have a function inside of a function, okay, we can actually find the derivative of that without having to FOIL it all out. But we are able to find antiderivatives for only a limited range of functions using power rule. We can sometimes use substitution to rewrite functions in a form that we can integrate. Okay, so basically U-substitution is the anti-chain rule. So when we did the derivative, recall that the differentiable functions given by y equals f in terms of u and u equals gx, the chain rule states that when you take the derivative of a function inside of a function, you get the derivative of the inside times the derivative of the outside with the function still inside. Okay, or what we call the inside-outside rule. So from that definition, the antiderivative means that if we start here with our inside-outside part, then the antiderivative is going to be our original function, our antiderivative of f with g inside plus a constant. Okay, so theorem 4.13, antidifferentiation of composite function, is basically the chain rule in reverse. So this part right here was in our original chain rule lettering, and this is what we are going to use to do U substitution. Basically, we're going to use U and substitute it into our function to get our function in terms of U. Okay, which sounds more difficult than it really is. Okay, so let's do some basic examples first. Okay. This is our first example. So I've got this function. Now, if I wanted to, I could sit here and I could FOIL all this out, x plus 2 times x plus 2 5 times, and FOIL it all out and hope to God I don't make a mistake, and then do power rule. Okay, but the first thing I notice, I have a function inside of a function. So what I'm going to do is I'm going to do integration by substitution. So I'm going to say, okay, just like we did when we did derivatives, when we started the chain rule, we said, okay, we let u be the inside function. Okay, so again, u is my inside function. So u is x plus 2. Then I'm going to take the derivative of both sides, very similar to what we did with chain rule in derivatives. So the derivative of u is du, and the derivative of x plus 2 is 1. Now technically I am skipping a step here, because you should end up getting du over dx equals 1, and then you multiply both sides by dx to get du by itself. Okay, and that's where I get here. Okay, but now what I'm going to do is I'm going to substitute my original function here. This is the integral of f of x dx, and I'm going to substitute it and get it in terms of u. Okay, so I'm going to replace x plus 2 as u, and that gives me u to the 5th, and I'm going to substitute dx in terms of du. Okay, now the variable of integration must match the variable of the expression. Okay, so if my derivative is in terms of u, then my variable of integration also has to be in terms of u. When you are done substituting, everything should be in terms of u. If you still have an x in your equation, something is wrong. Okay, then you didn't substitute correctly. But what this has done is it's taken this really complicated equation here and made it really easy, and now I can do just anti-power rule. So I take the antiderivative, add 1 to the power, I get u to the 6. Dividing by 6 is the same thing as multiplying by 1/6, plus my constant of integration. Okay, And then my last step is we need to substitute u back in to get it in terms of x, because we don't want, our original function was in terms of x, and our antiderivative should be in terms of x. So this is the antiderivative of this. This is that. And you can see how much easier and quicker it is to use U-substitution. Now this is a very basic example. They do get a little bit more difficult. Okay? All right. So here we go. Another one example. So this is where it becomes trickier, because again, when we dealt with derivatives in terms of u and did chain rule, u was always my inside function, okay? And it still holds true here. Since u substitution or integration by substitution is the inverse operation of the chain rule, u is still going to be our inside function. So in this case, I'm going to pick u, okay, to be my 1 plus x, okay? Not to mention, I also see that 2x dx is the derivative of the inside function. So do you see that? So when I take the derivative of 1 plus x squared, I get 2x. So that's also what's letting me know that u has to be 1 plus x squared, which means du is 2x dx, okay? Which makes my life super simple, because when I rewrite, remember, this right here, we said this right here is u, and this right here is du. So when I rewrite it, this is u to the 1/2, that's the square root, and 2x dx is now du. And now my function becomes much easier to take the antiderivative of, add 1 to the power, divide by the new power, plus c. And again, we cannot forget to plug back in u to get it back in terms of x. And that is my antiderivative. So this only worked because 2x was in the original, okay? So there are some, if that 2x, say if this was just the square root of 1 plus x squared dx, we couldn't have done U-substitution. Without that 2x right here, without this right here, this would not have been possible. Okay? Now, another one. Get some trig in there, because I know you guys love trig. So, for example, this, again, I'm going to use U-substitution. Now, notice when I look at this right away, I see x cubed inside of my sine function. And I see x squared here, which is the derivative of x cubed. Well, part of it anyway. Okay? So that's where I'm going to start. I'm going to start by saying, all right, u is x cubed. And then again, take the derivative, du equals 3x squared dx. Now, I see right away that this x squared is right here, but it doesn't have that 3. Okay? But we can fix this. It's just a constant. Okay? So what I'm going to do is I'm going to move that 3 by dividing both sides by 3. Now, this right here matches what I have right here and right here. And this right here is u. Okay? So what I've done is I've kind of forced my derivative of u by dividing both sides by 3 to match what I have over here in my equation. And so when I do my substitution, I get that 1/3, which is just a constant. So I did skip a step there, where this would be all of this right here. This and this is 1/3 du. But this is just a constant, so I moved it out front and left the du here. And then this is my u. Okay? But again, it makes my antiderivative really easy. The antiderivative of sine u is negative cosine u. And I just have that 1/3. And then again, the last thing I'm going to do is plug in my u, which is x cubed. And that is the antiderivative. Okay, so sometimes we have to force it a little, okay, and that's fine. We can do that. It's just a constant. Okay. All right. Let's do one more. So here we have our trig equation. Okay. Now, this one's tricky because the derivative of sine is cosine, and the derivative of cosine is negative sine. So how do I know which one to pick as my u? Well, this is easy. This sine right here has a fourth power on it. Okay. Now, again, one of those things that I've taught you guys is that as soon as I see a trig function with a power, remember this could be written as sine x to the fourth times cosine x. Okay, and when you see this power here, we can move it to the outside like that to make it easier. And once I do that, it's very obvious which one is my inside function. And in this case, I would be picking sine to be my inside. Okay, so once I do that, I say, okay, sine's going to be my inside, the derivative of sine, cosine, and look, cosine x dx, that's my du. Makes this problem super simple. Now I've taken this trig problem and turned it into nothing more than a power rule problem. Okay, and that's my antiderivative. So add 1 to the power, divided by the new power, and then don't forget to plug back in your u. The hardest part about U-substitution is, of course, figuring out what u is going to be. Okay, so here's some practice. So substitution in the general power rule, what would you let u in the following examples be? So in the first one, of course, remember u should be what is the inside function. So in this case, u should be my 3x minus 1. And you can see that the derivative of 3x minus 1 is 3, so I do have the derivative sitting there. Now the second one, I don't have a power like I do in the first one. In this first one, I had this 4 right here, but I don't have that in the second one. But what's telling me which one's going to be my u? Well, this one, 2x plus 1, is the derivative. So this is my u, and this is my du. So I could pick x squared plus x to be my u in the second one. Now, obviously on that one, you could just FOIL it out and do power rule if you wanted to. But I'm trying to get you to see that you're looking for where there's the function and its derivative. Okay? All right, so the next one, this one's really simple, very similar to our example. Since the x cubed minus 2 is inside the square root, that should be your u. Okay? Now the next one, which one should be your u? Well, again, I don't have a power or a square root or a trig function to see an inside function, and since there's just a fraction here, you really can't tell, but again, it's like the second one where I see, okay, I have 1 minus 2x squared, and the derivative of 1 minus 2x squared is negative 4x. So I see u and its derivative, so that u is 1 minus 2x. And the last one is very similar to the one that we did just a second ago. And I see cosine squared and a sine. So obviously cosine is the one inside, so that's what I would use. Okay, so really the hardest part about doing U-substitution is figuring out what u is going to be. Okay, now the last thing I want to talk about today is another method. Okay, this slide is basically a different method than I use. Okay, so some teachers teach it a little bit differently. Some teachers actually, after they find u and they find the derivative of u, they solve for dx by itself altogether. Okay, and this is this method. I don't necessarily like this method, but some of my students do. So I'm going to put this in here. So it starts off just the same, where we say u is x squared plus 1, because that's the function inside my quadratic. And I see that 2x dx there, and that is the derivative of the inside. So I get du equals 2x dx. Now this is where it would change. The way I would do it would be to change this whole thing, 2x dx, to du. But some train of thought says, okay, you know what? I'm going to solve for dx every single time. Get dx by itself. And that's going to give me du divided by 2x. Okay? Now, there'll be some times where I'll take that 2 out and have x dx but I will never move du's and dx's or x's on the same side and get dx by itself. It doesn't sound logical to me. But like I said, this is another method. So they substitute this way, and you can see this is going to be u squared, and this dx is going to be du over 2x. And now this is what I don't like about it. When you do your substitution, you're now going to have x's and u's in your equation, but these two x's will divide out with each other and leave you with u squared du. And this is what I don't like. I don't like the fact that when you're done substituting, you've got x's and u's in your equation that you have to divide out or do some kind of algebra to fix. I find it much easier and much more sensible to replace this with this and just have u's in my integration equation and not have to deal with this dividing out of these 2x. But again, I'm showing you basically what your options are, and that's another one. Okay, and of course plug back your u, and at that point it's the same. Alright, so these are two different methods. I personally don't like this method where you solve all the way for dx, but it's up to you. Tomorrow we'll talk about definite integrals and substitution.